page PDF homework on the computer. That's okay. He just emailed me saying, I'm going to deliver to you online because I cannot staple. So I like when my students come to me and mention that the difficulty in the homework was in stapling the number of pages that I have. I feel like energetic. I feel that I'm on the right path to be a good teacher, you know. This is what I like to hear. Okay, so you guys give it to me by the end of the class. So this is lecture 17, right? Okay, so the plan for the final 4 lectures that we have. I want to talk to you a little bit about Hilbert spaces with this chapter 5 of Brace's book. And then I will consider that we have satisfactorily covered chapters 1 to 5 of this book, which is already a nice functional analysis introduction, plus some additional topics. Maybe in these last 4 lectures I have time to talk to you a little bit about Fourier series as well, and Fourier transform, which I think is going to be good for your endeavors in the PDE class. Of course, there are some topics which I will be missing that I would like to talk to you about if I had time, which is chapter 6, touches a little bit about compact operators, and perhaps some Sobolev spaces, some Fredholm theory. But maybe Giovanni will do that in PDE, so that's okay. I'm choosing for this path. And when you learn about the Fourier transform, you have a little bit of a glimpse of what sort of research I do, because mainly I work in the field of analysis, but if you want to narrow down a little bit, the field of harmonic analysis is essentially the analysis behind oscillatory phenomena in nature. And oscillatory phenomena are usually modeled through some sort of operator like the Fourier transform. So this is kind of comes a lot in what I do. But before we understand more about the Fourier transform, we go to the general framework of Hilbert spaces, which for you guys, I believe, should be, after what you have been through in this course, it's actually a moment to relax, and it's going to be perhaps a piece of cake for you. So let's see. What are the basic definitions? What you guys, you certainly have seen this in your life. Well, let's just define it again. So first, I want to define the notion of a scalar product. And a scalar product is just, say, on a space, on a certain space, which we're going to call H, suggestive of being a Hilbert space. A scalar product is just a map A, or let's say, just say a map from H cross H into the real numbers. So we're going to put into the real numbers. You can put in the complex numbers if you want. Okay. So this is generally going to have this property. So it's actually a bilinear map that is symmetric. So we're going to denote with parentheses here. So UV is actually to VU. So for remember, every pair of vectors in H cross H, for every pair of vectors, I will associate a real number. It's bilinear in each entry. I'm saying that it's symmetric, and what I'm going to say, perhaps positive definite. Meaning that U is always bigger or equal than 0, and U is equal to 0 if and only if U is 0. Okay? So this will be a scalar product for us. So it's a bilinear, symmetric, and positive definite form in your space H. Okay? All right. Notation would be parentheses. Some books you will see a little dot. That is okay. Choose whatever notation you prefer. Just keep in mind that it's symmetric and positive definite for our purposes. Every time you have a space with a scalar product, this generates a norm. Okay, we'll see that. Okay, so every time, so a scalar product implies norm. And whenever we talk about a norm on a space with a scalar product, we mean the norm generated by this scalar product. So the norm will just be the norm of the vector u. If you have a scalar product, will be just this pair u square root. So I'm taking a square root of a non-negative number. So this gives me a perfectly well-defined number. Okay? Good. Now, it is obvious that this guy defined like this is always non-negative because it's the square root of a non-negative number. In case it is 0, then u, scalar u, is 0, which means that u is 0. So it's 0 only if the vector is 0. So I'm okay with that. But I have to prove the triangle inequality. Okay, so if you were here to prove, you'd say that, of course, norm of u in this case is bigger or equal to 0. Check. Norm of u being equal to 0 if and only if u is 0. Check. And then you are, okay, Emmanuel, you have said that this is a norm. So we actually have to prove the triangle inequality. The triangle inequality comes essentially for free if you recall the fact that whenever you have a scalar product, you have Cauchy-Schwarz inequality. This Schwarz has T or doesn't have T?
No. Not T.
No T. Cauchy-Schwarz inequality. Schwarz with T is another guy. It's also an important mathematician, but it's another guy. We have the Schwarz with the Z. It's Cauchy-Schwarz inequality. And the Schwarz with the T is a French guy, Laurent Schwarz, from the theory of distributions, the Schwarz class. So there are two different guys that lived 100 years apart from each other. But it's a very common mistake, as I might have told you. When I read papers and I'm about to referee papers, it's some of the silly mistakes that I point out to the authors. By the way, did you know that this is not the right Schwarz that they're quoting here? So what's the Cauchy-Schwarz inequality here? You have uv less than or equal than uv half vv. Every time you have a scalar product. And if you don't recall the proof of this, proof is very nice. It's just, you take the bilinear form, you just take, say, u plus tv, and u plus tv, wherever t is a real number. Okay? Being the same vector, w, scalar w, it's always bigger or equal than 0. But then if you use the linearity, remember, linearity, you have to use the linearity in each variable. So if you freeze one of the variables, it's linear in the other variable, okay? This is what bilinear means. So bilinear means if you freeze one of the variables, it's linear in the other variable in the sense that you can add up and you can multiply by scalars. Okay, so if I open this up, so if you freeze this, you can just open this up, and if you freeze this, you can open this up. So bottom line is that what you can do is, if you open this whole thing up, you get u scalar u plus, and then like first with first, this with this, you get t v scalar u plus, and then, so this with this, now, plus t u scalar v plus t square v scalar v. Okay? Since this is symmetric, what you get is u scalar u plus 2t u scalar v plus t square v scalar v. So what you have here is that if you fix u and v and let t be your real variable, you have a quadratic equation in t, something of the form a well, let's say your AT squared plus BT plus C. Right? This is what we have. We have a quadratic equation in T, which is always bigger or equal than 0. So if you learn in high school, whenever you have a quadratic equation that is bigger or equal than 0 for every real number, the discriminant, right, B squared minus 4AC has to be what? Less than or equal than 0.
Less.
Great.
Less than or equal.
Correct, right? My high school math is still okay?
Why less than or equal?
Because it's bigger than or equal here.
Ah,
Okay? You cannot have, you can have, for T you can have a root, but you cannot have two different roots. Because you cannot reach negative values, right? So B squared minus 4AC in this notation here will be less than or equal than 0. And if you just translate what the coefficients are, so B squared is your VV squared. If I'm not, no, I'm sorry. So B squared is just 2UV, so it's 4UV squared minus 4, and then A, and then C. Well, this is actually A, and this is C. Less than or equal than 0. So if you move this guy to the other side and cancel, so what you get is that UV squared is less than or equal than VV. Now you just take square roots on both sides, you get this inequality here. This guy may be negative, so if you want, you can actually put the absolute value. No problem. This is Cauchy-Schwarz inequality. Okay? Never forget this. Well, once you have this inequality, you can actually prove the triangle inequality for this norm. Okay? So if you want to prove the triangle inequality here, what you have to do is, well, let's see. I want to start with the norm of U plus V squared. This is what? This is just U plus V, scalar U plus V. I open this up the best that I can, and I get what? UU, VU, UV, plus 2UV, plus VV. Okay? So here I get what? Norm of U squared, plus here I get norm of V squared. And here I use the triangle inequality. I use Cauchy-Schwarz to say that U scalar V loses to the norm of U times the norm of V. So I get 2 norm of U, norm of V. And what I have now is just norm of U plus norm of V squared. So the norm of U plus V squared is less than or equal than the norm of U plus norm of V squared. Just cancel the squares and you have the triangle inequality. Okay? So here it is. So a scalar product, bilinear, symmetric, positive, definite form in the space. You must verify Cauchy-Schwarz inequality, and the norm that it generates by this relation. Well, if you define this, it's actually a norm. And the triangle inequality is an easy consequence of the Cauchy-Schwarz inequality. Good. So what is a Hilbert space? A Hilbert space is a space with a scalar product such that when I associate the corresponding norm, it is complete with respect to that norm. Okay. So this is just it. It's a vector space. So definition. H of Hilbert space. This one is just a vector space. H with a scalar product that is complete. So it's a Banach space to the norm that we just defined, right? So Hilbert space is just, if you say, Banach space with the norm coming from a scalar product. Right. I'm sure you are familiar with the lots of Hilbert spaces, but the most typical example would be if you have, say, an L2 of a measure space. And here, the norm, the scalar product of two functions u and v, would be just the integral over the omega of, say, u of x, v of x, dv of x. So if you are in a measure space omega with a sigma algebra and a measure mu. So this is the scalar product. It's obviously bilinear in each variable. If you take u scalar with u, you get the integral of u squared. My functions here, you always take real values, okay? So if I take the integral of u squared, it's 0, if and only if u is 0. This is then a scalar product. The induced norm, u square root, is just the usual L2 norm. So the L2 norm that we know comes from this scalar product here. So this is the typical example of a Hilbert space. If you say, Professor, I don't like to work with real numbers, I like to work with complex numbers, that's okay, no problem. You will just do this. This is your definition of the scalar product when you are in the field of complex numbers is almost the same, it's slightly different. You just change the symmetry condition by putting a bar. So it's like anti-symmetric in the sense that uv is just vu bar, okay? But other than that, pretty much the same. Okay, you just put a complex conjugate here. But let's say for the sake of simplicity that we'll be working with real valued functions. Okay, so this of course accounts for L2 of omega when omega is a subdomain of Rn. So the typical appearances of this is that when omega is, say, a typical subset of Rd, say an open subset of Rd, you can take the L2 of Rd, L2 of R, L2 of the interval 0, 1, whatever you want, but also this little space L2 of sequences as well. Little space L2 of sequences. Remember that it's just this space here when this omega is the natural numbers and the measure is the counting measure. Okay, so this is just the space of sequences, A1, blah, 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 AN, where the sum of the AN, AI square is less than infinity. And the inner product here, a sequence A, scalar sequence B, would just be the sum of AI, BI. That's the inner product or scalar product. When I talk about inner product or scalar product or dot product, I always mean the same thing, okay? So I don't have a preferred name, so I'll be switching from these three names. Don't mind about that. Inner product, scalar product, dot product. Okay, so L2 is our prototype of a Hilbert space. And in some sense, we prove that this is essentially the unique example of a Hilbert space. If they are separable, they have an orthonormal basis, and it will be essentially one of these examples, little L2 here. Let's see. So far, so good. Okay. So now let's capitalize a bit on what we know. First proposition is that a Hilbert space, any Hilbert space, H is uniformly convex. And then you know, uniformly convex means reflex. now on I won't write anymore that when I mention Hilbert space, of course I am underlying the hypothesis that we have a scalar product and the norm that I'm considering is the norm derived from the scalar product, okay? So just talk Hilbert space. Any Hilbert space is uniformly convex, hence reflexive. Proof. Very neatly, we have this so-called parallelogram identity, which essentially means that if I have, say, x plus y over 2 square plus x minus y over 2 square, what will this be? I think I'm correct in saying that, right? Let's just do a scratch computation here. X plus y squared is just x squared plus x 2xy plus y squared. This divided by 4. This will go away with this minus. So you get, yeah, you get that. All right. Please, please, this is not the length of vectors in Rn, but this is just, left, right, the bar is just a norm derived from the scalar product. For all computational purposes, you just can think of you taking scalar product on Rn. It just works general for Hilbert spaces, but the proof is more general. Is that clear? So you have this parallelogram identity, and this is one example. So therefore, if what you have is that if x is less than or equal than 1, and y is less than or equal than 1, and x minus y is bigger or equal than epsilon, remember this is what we have, right? To be uniformly convex, you want the ball to be round. So if you have x here, y here, with a certain distance epsilon between them, if epsilon is given, then their midpoint has to lie within a distance delta of the border of the circle, right? So the epsilon given, then with this thing, what you get? You get that x plus y over 2 square is less than or equal.
1 minus delta.
Then this is less than or equal than 1, right? 1 minus, and you move this guy to the other side. So it's epsilon over square over 4, right? So epsilon over 2 square. This is good. You already gave yourself some room. You take square roots and then you're fine. This is being uniformly convex. Good. So the space is reflexive. This is very, very, it seems that this concept of uniformly convex was actually made having Hilbert spaces in mind. Okay. Before we go and talk about the Rees representation theorem in the context of Hilbert spaces, which we kind of already know what's going to be from this, let's just talk about projections, because you may find this also in your life. So let's just... This was proposition 1. Maybe, let me say, proposition 2. Projections. So, if you are in a Hilbert space, so H is a Hilbert space, and K inside H is a convex and closed subset. Convex and closed subset. If, let's just say f is a function that is a point that does not belong to k, then there exists a unique u proposed to you in the exam, right? A unique probability such that f, the distance from f minus u, is the infimum or the minimum of the f minus v belonging to k. Right? And this guy is actually what we call the distance from f to the set k. So whenever I write distance from a point f to a set k is the infimum of the distances. And what I'm saying is that there is a guy that realizes the distance and it's unique. There's a unique guy that realizes the distance. Moreover, such u is characterized, let's write it this way, completely characterized by the following inequality, which is characterized by the following inequality. And what I'm going to say is that f minus u, v minus u is less than or equal than 0 for every v in k. This is in alignment with what we know already from RD with our geometric intuition. So if this is my set K and this is my point F outside, there will be a guy here that realizes the distance, which I'm going to call U. And what I'm trying to say is that if the U is the guy who's closest to F, and I take any other guy, say V here inside, these two vectors, F minus U and V minus U, will have an angle which is more than 90 degrees, right? This is what this is saying. If it were less, then this U would not be the closest point. Okay, so this is the geometric interpretation of this thing. Okay, whenever all of these things happen, you may find the notation that this U is the projection of F over K. Okay. Let's see if you guys are studying for this course. So we can prove, say, the existence of a minimizer, the existence of a point that realizes the distance in many, many different ways. Okay?
Reflexivity is enough. Reflexivity is enough for existence.
Yeah, so let's just vomit here some of our previous knowledge. So what would we do if we wanted to invoke some of the weapons that we have already learned? So if you wanted to prove existence, so what you do is that you have your convex compact set here, K, convex and closed set here, K, you have a point F outside. I want to prove that there is a guy here that realizes the minimum distance. Okay, so let say D be the distance from F to K. It's a finite number. Okay, since K is non-empty, probably we should say K is non-empty somewhere there. And let's say UN be an extremizing sequence. What do I mean by an extremizing sequence? Well, since this is the infimum of something, there's always a sequence that tends to that infimum, in the sense that D is equal to the, say, inf over n of this distance f minus un. Alright? So at this point, you wanted to somehow show that your un converges to somebody. But I don't know, it's an infinite dimensional setting. You might have un pointing in different directions, so it's a bit unclear what you should do now. But no, I mean, but we have seen, or we have many ways to go around the situation. You can use the uniform convexity of this thing. So it's actually a statement that holds in general. Not only if you just erase your Hilbert space and replace by any uniformly convex, the statement up to here holds the same. It's one of the exercises, I guess, in the book. But let's say in this setting, let's try to use my favorite theorem, functional analysis. Let's say,
weakly convex.
yeah. So this is in particular, this UN being an extremizing sequence, it's a bounded sequence. Why is it a bounded sequence? Because you can draw a big ball here, so you can just say that UN minus F is less than or equal than, say, D plus 1. So if the infimum is D, they will all fall in the ball of D plus 1. So they're all bound. It's a bounded sequence here. So being bounded, and this implies that there exists U and K. There exists a subsequence that converts weakly to somebody U. So here I'm using that the space is reflexive. Reflexivity. And now what? Now you can use, and this U, okay, so I'm going to use two facts here. First, so if you have a bounded sequence, it converts, there is a subsequence that converts weakly to somebody in your space, H. So this U here is born on H. Okay. Another fact, I would like to show that this U actually belongs to K. Yeah, exactly. Then you have to invoke another result that we have proved. This set here is convex and closed in the strong topology. It means that it's convex and closed in the weak topology as well. So if a sequence converges in the weak topology, the limiting point has to be inside. So this belongs to. So I'm using here the fact that it's reflexive to use the result that a bounded sequence has a weak limit in the space. And then I'm also using the fact that my original set is convex and closed. Then it doesn't mean if I'm talking about the strong topology or the weak topology. In any case, this limiting point U belongs to K. Okay. And then you just use the fact that, say, we have proved that for weakly convergent sequences, the norm of the limit is less than or equal than the limit of the norms of the guys in the sequence. So if UN converges weakly to U, of course, F minus UN converges weakly to F minus U. And this is less than or equal than D on one hand, right? Because this limit is actually D. But this is always bigger or equal than D because U is a point in K. So therefore it must be D. So here's one way to prove using what you know about weak convergence already. You can take a look at two other different proofs in the book. So we have proved that there exists a guy. Now let's try to evaluate the uniqueness of this projection. So far, so good? Good. Okay, so so first prove the existence. Now let's prove the equivalence between these two statements. So I want to prove now the equivalence between the fact that F minus U is the infimum of F minus V belonging to K. This is equivalent to F minus U, V minus U being less than or equal than 0 for any V in K. Let's prove the equivalence between these two facts. How do we do that? let's see. Suppose we want to show this direction. Okay? Suppose that U is your point that is one of the points. We haven't proved that it's unique, but it's one of the points that extremizes the distance. So take any V belonging to your set K. There's not a lot that you can do. You can just say that F minus U is less than or equal than F minus V. That's all you can say. And you can square this, and you can hope you get this. It's the only way. Right? Let's see. What's this condition here? You get F squared minus 2FU plus U squared. Maybe I'm wrong. Maybe less than or equal than F squared minus 2FV plus V squared. So F squares cancel. This implies that so if I move, let's say, everybody to the left-hand side, what do I get? 2F V minus U. Is that okay? Plus U squared minus V squared is less than or equal than 0. Now, maybe this is not what I wanted, right? It's almost there, but not what I wanted. I have F and I have UV. So this is not what I wanted. What do I want to do? FU. Okay, this is, I get F V minus U, that's okay, and I have minus UV minus plus U squared. So I'm almost in the good direction. So we might have to use some sort of Cauchy-Schwarz here. How do we do that? Let's go second try. Second try. Let's see what we have to prove. What we have to prove is that F.
Actually, we can just use the Cauchy-Schwarz with we have U, the scalar product UV is less than modulus of U.
Yes.
So if we take the negative, just the inequality we want to prove, we can separate it. F, the scalar product of F with V minus U minus U and V minus U.
This is here.
We have one of them, and minus U and V minus U, it gives us minus norm of U squared.
Yes, which
And
would be here.
Yes, and we get minus VU, and here we use Cauchy-Schwarz.
Minus VU, you change
Yes.
by U times V.
We have minus VU, that's greater than or equal the norm of U multiplied by norm of V squared.
So let's see if what you're saying is that we have to prove this thing, so F U minus V loses to U against V minus U. Is that correct? This is what we have to prove, right? If I just move this U to the other side. So this is 1. This is what I have, right? This is what I have if I did that. And this is what? This is uv minus u squared. I'm almost there.
This is the equality photo of Cauchy-Schwarz inequality, this condition. This is because if we take f minus u and f minus u must
Which one? This one?
no, is the condition is this one. This one in the right hand side. This is the equality condition of equality case of Cauchy-Schwarz inequality. See f minus u, v minus u is smaller or equal to 0. It means that f minus u, we can take u, v minus u is equal to f minus u minus f minus v. So f minus u is smaller than f minus u or f minus v. F minus u norm is square, is smaller than f minus u and f minus v. We know f minus u and f minus v just smaller than f minus u norm square and f minus v norm square. But if f minus u is equal to infimum, so in this case we have to prove this is the equality case of equality false of
That's what we are trying to prove. But you see a direct way to do this? I'm trying to say that, well, we have to prove this thing. Let me see how I would like to argue with this. So this is what we have to prove. This is less than this guy. What we have if we did this would be less than or equal to minus. We would have this. We would have this, but this is not less than this, is it? This is not less than this. It's slightly different. Did I do something wrong? No, right? Let's see.
Actually, we did something wrong.
Did I do something wrong?
I think you cancelled minus because here we have. No. It is okay.
I think.
Let me try a different way. Let me erase it.
I think.
Taking if v belonging to k, let me try a little bit about this. So let me consider the vector omega, which now connects u and v. So let me say this. Let's call this guy. This is what we want, right? Let me say take omega to be what? To be t. Something like this. So tu plus 1 minus tv. Is that what I want?
So.
I want just to take u and do a little bit of a bump in this direction. So when t is 0, so I would like to make t approaching 0. So let's try to find a combination of this. Okay, let's try to find a combination of this. So suppose I take a t very small, so that will be close to u. Then I'm taking in the direction of certain vector of v. So when t is 1, I get 1 minus v. Yes, it's still not what I want, right? So let me just take, tv plus 1 minus t u. So I'm going to connect these two guys. When t is 0, I'm at the u. When t is 1, I'm at v. Let's just see what this happens here. So for this w, f minus w is less than or equal. It's bigger than or equal than f minus u, right? I'm going to square both sides. Let's see what that gives me. So this is f minus w is with this guy, so f minus tv minus 1 minus t u squared is bigger or equal than f minus u squared. Now let's open this whole thing up. And what we get is would be just better if I just write this as u plus t that multiplies v minus u. Okay, so let me just write it like this: u that multiplies t v minus u. That is fine. Okay, so just write it here: f minus u minus t v minus u. This is w. When I open this up, this implies this is f minus u squared minus 2t f minus u v minus u, right? Plus t squared v minus u squared. And this is bigger or equal than f minus u squared. Now I cancel the f minus u, and I have some polynomial here in t, which is bigger or equal than 0. I'm going to pass to the other side, so I'm going to have t v minus u is less than or equal than 2t f minus u v minus u. Okay, so now I'm done, right? T is, so let's say t is between 0 and 1. So I can just cancel the t here.
I think
This is t squared, right?
the sign of the equality is reversed.
Side is reversed.
Yeah. T squared v minus u squared is greater.
Bigger than this. I will cancel my t. So I get t v minus u squared bigger or equal than 2 f minus u v minus u. Since this holds, since this is good for all t's bigger than 0, we can just move t to 0. And this implies that 0 is bigger than f minus u v minus u, as we wanted, right? Okay, so in this sense, in this regard, this is some sort of just limiting argument, just taking in the neighborhood of u in the direction inside your convex set, if you want. It's kind of like taking the derivative in that point. Okay, good. This is one side of the argument. The other side is we proved this. Now let's prove the other way around. So assume this holds for all v's, and let's try to show that u is the minimum. Well, how do we do that? Is there a way that we can come back here? If we start from here, it's bigger than 0, then we cannot put this, right? No. So there's a different way. So suppose this was for all v's in k. What do I want to do?
Actually, we can put it because t is positive and this other thing is not negative. So
Absolutely, yeah, you're right. So if I start from here, I can just say, okay, this is less than 0. This is certainly less than a positive number, right? Then I can just multiply both sides by t, which is a positive number. Then I go to this line, and I go to this line. So I guess that this is true for any t between 0 and 1. In particular, t equals 1. And then I get f minus v. Okay, so it's just come back in the previous argument. And take equals 1. Is that clear? If I start with this for any v in k, I can certainly come, this implies this line. Since this is less than 0, this is less than this positive number. V is given in K, and I multiply by T, this is less than this positive number. I add up on both sides this quantity, and rearrange the terms, so this implies this, which implies this, which implies this for any W of this form. Now I just choose T equals 1, and I get V. Okay? So this is actually, this is just if and only if and only if, this is if and only if, this is if and only if, and this is, well, if and only if as well. This is true. For all T, this implies this thing. Are we good? Good.
Why are you not putting a reverse?
And this, well, this for all T holds if and only if this is here. But this is for a particular T, it doesn't have to be this.
Yeah.
But for all T, it's okay. So let me just say that. So what you want to do is just essentially start from this line and just come back with T equals 1. Okay. But this will only implies this if this is good for all T, not just for a fixed T. It's just a chain of
But
equivalence.
actually, for all T greater than 0, it's also true, because we have 0 is less than T multiplied by the modulus, because both of them are positive now. The modulus is non-negative and T is non-negative.
No, well, you're right. What I'm trying to say is that this line here for a particular T does not imply this line.
Ah, yeah, yeah.
This line here for a particular T, just this line here just implies this line if it holds for all T bigger than 0. Okay, of course, this implies this for any T. This doesn't imply this for any T. It's just a subtlety. That's okay. Are we good? Good, let's move on. So what's the final part? So we proved the equivalence between these two statements. Now let's prove the uniqueness using this statement here. Let's prove the uniqueness using this statement here. Well, so again, this U, if it satisfies this thing, it satisfies this thing. So suppose you have two. Suppose U1 and U2 belong to K. Verify. Let's call star. Star is any one of these two. Then you would have what? F minus U1 scalar V minus U1 is less than or equal than 0 for all V's in K. And F minus U2, V minus U2 is less than or equal than 0 for all V's in K. So all you have to do now is to pick some interesting choices.
U2, U1.
So you'll pick in the first line a particular V. You'll pick U2 here, and in this one you'll pick U1. So if this implies that the first line, F minus U1, scalar U2 minus U1 will be less than 0. And the second line, F minus U2, you choose V here to be U1, so U2 is less than or equal than 0. Is that okay? Now, I will take the second expression, it's here. The second entry is almost the same. It's U2 minus U1, U1 minus U2. What I'm going to do, I'm going to change the signs here. But I cannot just change the sign in one entry, I have to change in the other one, too. Okay? So, what I will do is that I will change here and here. Now it's okay, it's the same number. Okay? So remember, it's bilinear in each entry. So if I multiply by minus 1 in one entry, minus 1 in the other entry, minus 1 times minus 1 is 1. I'm trying to teach this to my son, that the enemy of my enemy is my friend. This is how we learn this, you know. This is 1-1, so the friend of my friend is my friend, the enemy of my friend is my enemy, the friend of my enemy is my enemy, the enemy of my enemy is my friend. Now you made the second entry the same, you just add them up. Okay, so when you add them up, what you get is what? U2 minus U1 scalar U2 minus U1 is less than or equal than 0. So what you get is the norm of u2 minus u1 squared is greater than 0. Of course, this can only happen if u1 is equal to u2. Okay, so this variational condition here implies the uniqueness in this case. Right, this finishes this proof of this very nice result. If you are in a Hilbert space, if you have a closed and convex set and a point outside, there is a unique point that realizes the distance. This is called the projection of the point into the subset. Okay? This is particularly interesting in the case where you have actually a subspace. So when you have a subspace, this is called the projection of the point in the subspace. Is this good? Good. Go ahead.
We didn't use the uniform convexity. This proof, actually, I think this proof only for Hilbert spaces.
We didn't use the uniform convexity. Yes, we
Uniqueness for uniqueness.
for uniqueness, no.
And so we can prove as well.
But we use the structure of Hilbert space, right? We use this thing here. So in some sense, we're kind of using in disguise. Yeah. Okay. So yes, we are using, but in this we are using the Hilbert space structure. So be careful when you say that you're not using uniform convexity. You are using it in disguise. Good. Okay, so let's see. What's the number of my proposition? Maybe 3, right? Proposition 3. Projections do not increase the distance. So under the same conditions as before, let's say I want to show that f minus g is bigger or equal. Let's just say that projection of f over k minus projection over g over k is less than or equal than f minus g. So if you project two guys into a convex and closed set, these projections do not increase the distance. Is that reasonable? That looks reasonable, right? And the way to do this, again, is to put the, let's call U1 to be the projection of F, and let's call U2 to be the projection of G. So by the previous proposition, we know that F minus U1, V minus U1 is less than or equal than 0, and then F minus G minus U2, V minus U2 is less than or equal than 0. This is for any V in the set. You again choose this V special to be U2. You choose this V here special to be U1. Let's change the signs here again. Plus, minus, and we add them up. When we do this, what we get is, on the left-hand side, F minus G minus F minus G plus U2 minus U1, and U2 minus U1 is less than or equal than 0. Is that reasonable? Yes, just adding them up. Then this implies that, well, U2 minus U1, U2 minus U1, I'm leaving this, it's less than or equal, I'm moving this to the other side. So it's G minus F, U2 minus U1. But then this is just U2 minus U1 squared, which is less than or equal than, and this side, well, G minus F, U2 minus U1. And now here I can use Cauchy-Schwarz, G minus F, U2 minus U1. If U2 minus U1 is 0, there's nothing to prove. 0 is less than anything. And if it's not 0, then I can cancel. these projections, they do not increase distance. And, okay,
Is it a linear map?
it's a linear map. Well, generally if you project on say some sort of curved compact thing, it's not a linear map, but it's a linear map if you project into a subspace. Okay, so now the special case is that position 4. So the special case when K is a subspace. So if you are K a linear subspace, closed subspace, it's obviously convex. Every subspace is convex. So if it's just linear and closed subspace, what you have is that the extremizer U is then characterized by the condition F minus U scalar V equals 0 for every V in the space. Just characterized by this condition. And the map, projection map P from the Hilbert space H to this subspace K is linear and continuous. How about that? So if you are now in a subspace, that's your K, have a point F outside, the picture looks nice. So this is your U, the projection. So first I want to prove that it's characterized by this condition, which is slightly different than before. So before I had like F minus the minimizer, scalar V minus the minimizer, the angle was more than 90, the scalar product was less than 0 for every V. Okay, so we may start from that, so proof. We already know that F, so remember, F is always a point outside, U is the projection here. So F minus U, scalar V minus U, is less than or equal than 0 for any V in K. Alright, so we already have that. Now, since my K is a subspace, well, I can just multiply here by T, a real number. TV. So if V is a guy in my subspace K, T times V will be there as well. Now let's open this thing up. So if we open this up, we get T times F minus U scalar V is less than or equal. Then on the other side I have F minus U scalar U. For any T. Now since this holds for any T, T times a certain number being less than or equal than another number fixed can only happen if I send T to infinity or minus infinity. This can only happen if this number is 0. Okay, so this implies that F minus U scalar V, since this holds for any T, this implies this is 0. Okay, so the condition that we had before applied to TV, where V is fixed and T varies, implies this condition. Now, this condition now, F minus U scalar V for any vector V in K, obviously implies this condition here that we had before, F minus U, V minus U, because if V is in K, V minus U is in K as well. And if this is 0, it's obviously less than or equal than 0. Okay, so condition before implies this one, and this one is actually stronger than the one before. So not only has to be less than or equal than 0, but it has to be equal here. Good? So in case you have a subspace, you have this very nice and stronger condition. And this actually helps to prove that the map is linear. So now let's show that P is linear. So if you have, say, so this implies that f minus the projection of f over k scalar any vector is 0 for any vector v in k. G minus projection k, projection of G in k, scalar v is 0 for any v in k. You just add them up and you have f plus g minus this vector pk of f plus pk of g, scalar v is 0 for any v belonging to k. But remember, there was a unique vector that verified this property for all v's. We already proved that. So this implies that pk of f plus g, which was the unique vector that verified this, is actually equal to pk of f plus pk of g. Alright? This is one. Well, trivially, you also get that pk of lambda f is lambda pk of f. Therefore, the map P is linear. So it's a linear map. And also, it is continuous. Continuous means bounded because we have proved that it does not increase distance. So pk of f minus pk of 0 is just, on one hand, is just pk of f because 0 is in the set, so pk of 0 is 0. And we have shown that this is less than or equal than f minus 0, which is just f. So I'm showing that pk of f is less than or equal than f. Okay, so it's here you have projection into a closed subspace. All right? Good. Questions so far? This was just a basic introduction. So we have shown Hilbert spaces, what's a scalar product, what's a norm, it's reflexive, and now we have studied the projections a little bit. Let's just conclude the class today proving that the dual is itself the Rees representation theorem. How about that? Theorem, again, another manifestation of the Rees representation. The dual of a Hilbert space is very, very easy to describe. Okay? They're just scalar products with other elements in the space. Okay, so let phi be a guy in the dual of the Hilbert space. Then there exists a unique, say, F in the Hilbert space such that phi acting on V is actually equal to the inner product of F and V for all V in the Hilbert space. Moreover, the norm of phi in the dual space is actually equal to the norm of F in the Hilbert space. So the linear functionals are given by inner product with some fixed guy in the space. Okay?
These give a natural mapping from the space and the CD1, right?
Yes, so H now will be isometrically isomorphic to H star. Okay, so the mark, you can always identify this. There's an isometric isomorphism from H to H star. Right, this again, it doesn't mean that they are equal as sets, as I was telling the other class. But there is some isometric isomorphism between these two spaces. Like the spaces if I have an isometric isomorphism between two spaces, one might still be a proper subset of the other. I just take the space of L2 sequences and shift to the right and put the 0 in the first entry. The spaces are isometrically isomorphic, but one is a proper set of the other. Now, the proof of this fact we have already done in the previous class, so let's just remember. So every guy like this defines a function. So let me construct that map T. So let us construct the map T that will go from H, from the Hilbert space, into its dual. For every function u, for every element u in the Hilbert space, I will assign an element tu in the dual. Then I have to tell you how tu acts. I'm going to tell you that tu acts on V. This is brackets because tu is a guy in the dual, acts on V by just defining it to be u scalar V. Okay? So this is my map. We will show that this is an isometric isomorphism. Yeah, first I have to check that this guy Tu that I defined here actually belongs to the dual. Right? So the fact that Tu acting on V is equal to u scalar V. So this is obviously linear in that entry V, right? I can just change V by V1 and V2 and spread out, or lambda V. And it's actually bounded. Bounded because you have that this is less than this number times the norm of V. So this actually implies that T of u in fact belongs to H star. Okay, Tu defined like this actually belongs to H star. It's an element in the dual. Okay. Now the map T is linear if you just take u1 and u2. T of u1 plus T of u2 is T of u1 plus u2. So the map T is linear, and it's also bounded. Right? Remember, norm of Tu in the dual is equal to the supremum of Tu acting in V, when V belongs to the Hilbert space and has norm 1. Okay? But then, of course, this is less than or equal than by this inequality, right? Okay. So the norm, so it's a bounded operator that the norm of T of u in this target space loses to this number, which is the norm of u in the original space. So this is a bounded operator. This T map is actually linear and bounded. In fact, this can be made to, this is, in fact, this is equal by choosing a specific V. What is the V that I have to choose? Well, it's very simple. What's the V that realizes the equality in the Cauchy-Schwarz here? U. Just U, right? Since I have to normalize to have norm 1, so let's just choose V to be U over norm of V. Okay? So this is a unitary vector that realizes the equality here in the Cauchy-Schwarz inequality. Okay, so I'm going to promote this inequality. So this map actually is an isometry. So I have here an isometry from T into H star. Being an isometry means that it's injective. And all I'm left to do is to actually prove that it's surjective. Okay? This implies that T is isometry hence injective. We claim that T is also surjective. We have already seen this proof in the past class, which is just, we're going to use the fact that the space is reflexive. Okay? So how do we show that such a map is surjective? We know that P of H is a closed subspace, right? Because it's an isometry. If some things converge on the image, you bring it back to the original guy, and they converge here, therefore the image is closed. So to prove that it's surjective, you just need to show it is dense. If you have a closed and dense set, then it will be the whole space. How do you show that a subspace is dense? Subspace of H dual is dense. You get the guy in the dual of this, such that it vanishes in the subspace, then you have to prove that this functional is zero, right? So we must show that given a functional phi belonging to H dual, such that phi acting on Tu is zero for any u in H implies that phi is zero. You have to prove this. Take a guy in the dual of where you are and act in everyone in the subspace. If this is zero for everybody in the subspace, then your functional has to be zero. You have to prove that.
Yeah, but this turns out to be if u, the scalar product uv equals 0 for every v in v, then u must be the zero vector.
Yes, exactly. Right? So now we use the fact that since H is reflexive, say H is reflexive, what do I know about this phi? Phi is the J of somebody, right? It's the J of V for some V in the space. Recurrent map J that goes from H to H double star, right? So now what I'm saying, what is J of V acting on the functional Tu? By definition of the J map, this is T of U acting on V. T of U acting on V, by the definition of this pairing, is just U scalar V. So what you're saying is that this is zero for all U.
Particular.
In particular, you can take, just take U equals V, and hence, well, this phi must be identically zero and the space is dense. Okay? I hope that you guys can appreciate that we are already using, along this course, lots of little facts that we proved in the first classes, which is, if you arrive here on the first day of class and I show the proof like this, there will be a lot of blank spaces. Wow, why this happened and so on. There's a lot of little instances where, even without knowing, we are using harmonic theorems here and so on, but we have proved these things. But this seems so far, far away that we don't even remember anymore. But the harmonic is behind, for example, this fact, right? So it's very nice. Questions? Good. So let's finish the class here today. We'll continue on Friday. Let's do one more class about this chapter on Hilbert spaces. Next class, I perhaps want to talk a little bit about the Lax-Milgren theorem. Might want to give you some introduction to PDEs and solar spaces, just to give you an idea how this is used, and talk about orthonormal systems. And then in the final two classes, we talk about Fourier transform. Well, that's good. See you guys on Friday. You have homework to deliver to me, and I don't have... Take a break. I will be assigning some more homework later on. Take care.